Yeah, thank you very much, Manuel, for giving this nice introduction. And everybody knows I'm super happy to be here. And everybody knows I stayed in the hotel even. I have now a home like 10 kilometers from here. So in Niederalm, which is more or less the next village. Okay, so I'm super happy. Therefore, I'm always happy if Gyro invites me to nice parties. But I have to deliver now the talk because it's a surprise for the nice parties. Okay, this is all recorded. I should be careful what I say. Okay, so I want to talk about Kagome lattice, and I forgot the advertising for Quast, I have to say. And I for sure have to say that I like Gyro's initiative of SPICE, and since I feel strongly connected to Mainz, where I was a professor for some time. Okay, so we don't leave topology. Don't be worried if you see the title, frustration. Okay, so because I think seeing the things through the viewpoint of topology simply has changed totally how we look for materials and how we find maybe even interesting materials for application. So, so everybody knows, and now I have to look how this works with the. Now here it is. Everybody knows the ingredients of topology is simply the band inversion. So if you would have a simple semiconductor, you have a valence band and a conduction band, but you can have also overlapping bands. This is a semi-metal. And then depending from the symmetry, we can have forbidden crossings here, which leads then to a band structure like this, where you have a part here of the conduction band and the valence band and vice versa. And you have this nice surface states which lead to this very special insulator. So normal insulator here is simply like the grain of salt, but here you can have this topological surface state, which where the spin and the orbital, the momentum of the electrons are locked. And this is very similar to the quantum Hall effect, where you have also at the edges, so you have a two-dimensional electron gas, and then at the edges you have electrons. In a high magnetic field, you have electrons at the edges where the spin and the momentum is locked, and they are topologically protected. So if I make an edge here into this 2D deck, or in this device, so I don't destroy these electrons, so they simply go around the corner. So this is very interesting because now we can go beyond the quantum Hall effect. So when you talk to Klaus von Kitzing, he always thought it's an exotic phenomenon, but now we have it in many, many materials. So having band inversion, if somebody looks for band structures, is some common feature. And if you even don't look for the bands around the Fermi energies everywhere, so it's an inflation, and this is exactly what we observe. So, and beyond of the simply looking for the band inversion, here I have to learn to use the pointer, sorry. So the band inversion, so you can have here this area of forbidden crossing, and here this forbidden crossing open up the band gap, especially if you have spin-orbit couplings, and the spin is not a good quantum number, and we can have this topological insulators on one side. But depending from the symmetry of our crystal, we can also have some degeneration points here left over. And depending if it's a high symmetry point, we have Dirac semimetals, or if it's a low symmetry point, we have some Weil semimetals. And especially these Weil semimetals are super interesting. Beyond this electrons where spin and momentum is locked here on the surface only, we can have here electrons which are chiral, and I'm very much interested in chiral electrons nowadays, so in the bulk of the system. So at these crossing points, we have electrons which are chiral, because if these Y points come in pairs, and so you can have, you always have two Y points, and they have different chirality in the electrons. And the other feature, what we are looking then, is for the Fermi arcs at the surface of the material. So why is this chirality of the electron so interesting? Because this connects to some fundamental properties, and I still have to do advertising for this. This is a chiral anomaly, which is in the interest of high energy physics, and therefore we are working on chirality, even if this is not the main subject of the talk today. But I think there are SPICE talks of me about chirality, so you can watch them up. But the interesting thing is that this is a fundamental broken symmetry. So it's like the parity violation in the weak force. So you can explain some fundamental asymmetries, like, for example, the asymmetry between particles and antiparticles in the universe. And this is not proven yet, so people try to do it with high energy experiment with heavy ion collision, that you can have this Dirac equation as the origin of the asymmetry between particles and antiparticles. But in solids, you can use the same Dirac equation and do a similar observation if you use electrons and holes in a Dirac semimetal in a magnetic field or white semimetal where we have this chiral electrons. Very similar what we can know from chemistry. And this allows under certain circumstances of a measurement an asymmetry between particles and antiparticles, and you can even find this in Wikipedia. And there was a Nobel Symposium where the chiral anomaly was a special issue, but so far people really are discussing whether we already in solid state physics have proven the chiral anomaly. So I still think it would be nice to have something, a unique proposal from the theory, like a quantum effect. So Marco, I'm still waiting, okay, where we could measure it. So, but seeing this band inversion is now, you are not surprised that we can do this for all the materials and that we can say of the existing materials, and especially because metals have many spaghetti bands, that 30% of all inorganic materials are topological, and we simply have to figure out whether material is topological or not, or what we can do then, what can we absorb, which is interesting. So, the Kagome lattices are very much connected with magnetism, and especially also in magnetic materials, we have the situation that we have every crossing point is a Y point because we break time reversal symmetry. So therefore, I'm surprised that not more people look for magnetic materials, but everybody loves magnetic materials here in the room. So more or less, there must be an inflation of interesting topological material. So instead of 230 space groups, we have 1,651. And we gave this review about the already known topological materials, but there are many now general papers where they have analyzed all the space groups and looked up which space groups are very good for very good topological materials and which not. But I would say, honestly, the magnetic materials is an inflation. So you simply have then to look that you dope it eventually to the right points. And I want to talk a little bit about this. So there's a list of some antiferromagnetic materials, and this was a paper which we already published in 2020, so it's old work. But you find here only the antiferromagnetic materials, and this was only 500, and why? And why are these certain compounds? It's very simple, because there are not so many crystal structure plus spin structures of antiferromagnetic materials known. So therefore, it's not so surprising that we find especially fancy materials where people already are interested, like the iron pnictide superconductors here, because for sure people were interested to know about the spin structure here, and some other compounds, especially in heavy Fermi ions, so you can know better. But the point is simply we need more neutron data from single crystals of magnetic material. We should do it even if you think you have a boring compound. I'm sure it's not boring, you know. But we have to know the spin structure. Yeah.
Sorry, I didn't understand your last point. Why is it so much harder to form antiferromagnetism than ferromagnetism?
No, but I think in a ferromagnetism, the spin structure is often like this, eventually. Yeah. But the non-collinear is also not well investigated. But this is very easy. You assume, and all the transport measurement fits to this. But if you have an antiferromagnet, you don't know the spin structure. So therefore, I simply say we could only investigate 500 compounds, because from all of the antiferromagnetic compounds, only of 500 compounds, we could rely on the magnetic structure. And I simply want to do advertising for the neutron people to do more neutrons, okay?
Right, okay.
So simply to really get out of this interesting stuff. And there's a lot of hidden. We know this from altamagnetism is now a very popular field. So also there it's sometimes difficult because we have to grow big single crystals, but Silke and me, we are working hard on this, and probably many others. But this is the explanation why we look for certain classes of material. And you will see here's already some Kagome lattice compounds are here. This is a Kagome lattice, this is Kagome lattice, and probably more of them are Kagome lattice. So I can tell you today, we talk about an inflation of Kagome lattice. Okay, there you can have also many other interesting properties. Okay, so we personally investigated, and this is a figure out of the review, already a certain number of magnetic compounds. Some you will hear about in this talk, because this is a Kagome lattice and this is a Kagome lattice and so on. And what you can do if you have this magnetic compounds, you can do a lot of interesting stuff. So the simple thing you will learn, so we measure the anomalous Hall effect and the anomalous Nernst effect. I explained already to you the chiral anomaly, but the chiral anomaly you will see is so far the proposal was that you should find a negative magnetoresistance effect. And if I talk to Manuel, in a magnetic material, there are everywhere negative magnetoresistance effects. So we were forced to measure it in one Kagome lattice. This was the first magnetic wild semi-metals, and the editor of Nature Physics wanted to see it. It's a highly cited papers. We did it, but we didn't believe by ourselves that this is really the chiral anomaly. Okay, but anyway, so with the chiral anomalies, there's this. If you do thermal transfer, it's a gravitational anomaly. So this is really still some big question mark. So, and the other thing on this side is the quantum effect, the quantum anomalous Hall effect, and the axion electrodynamic, the axions. So these are still things which people are very keen of, also in, again, high energy physics at this meeting, so especially about the axions, and I think there's a lot to do also having better crystals and so on. People like Frank Wilczek in high energy physics would like to see that, and I think he really expected that the chiral anomaly and this stuff maybe leads to a Nobel Prize. If not, the people fight too much against each other. Anyway, still to do. Okay, there are some results. Kagome lattices are very interesting. For what reasons? People looked in insulating compounds already about this very nice pattern, you know, which you know even from art. And so because you have this triangle, you have also magnetic frustration if you have a arrangement of the spins in the lattice. But now under the viewpoint of topology, we don't only look for the simple magnetic frustration. We simply can say the simple band structure of a Kagome lattice is this. And so I already explained to you that Dirac points are very interesting. But on top, we have Van Hove singularities, which people as old as me, the boomers, know. It's interesting for superconductivity, okay? And we have these flat bands where people are super excited, like Andre Brunevik now are more excited about flat bands than Van Hove singularity. You can fight about this. But you see, this is a fantastic band structure for physicists. No? You combine topology and superconductivity and correlation. Huh? This is a dream. So let's look for Kagome. So far, the people looked for systems where you had the Fermi energy here. For insulators, it was in the gap, like the Herbert-Smith one from which was our friend Rosa Valenti worked about this, and they hoped we can dope it. But I think a really strong insulator is very difficult to dope, maybe if you make some film. Anyway, so this is very interesting. So for us, there's even application, and I always look for application. So it's like, because one way also to really give a value to topology is simply if you look to the Berry curvature. So I love the Berry curvature. We do a lot of calculation because then you see where you have to dope your materials to which point. And so if you do a simple calculation of the Berry curvature, you see that at these crossing points, you add spin-orbit coupling, you get enhancement of the Berry curvature. And this is very interesting because properties which are related to the Berry curvature and which are known in magnetism and in spintronics, especially like the anomalous Hall conductivity and the anomalous Nernst conductivity, were thought they go linear with the magnetization. But with the Berry curvature, we understand why it doesn't go linear with the magnetization, because the Berry curvature is directly related to the anomalous Hall conductivity. You see a peak. And in the Nernst effect, you see also an enhancement. So if you want to maybe do thermoelectrics, you should think whether you use this concept to do nice thermoelectric materials. So, and this is, again, this nice review, also with Gyro Sinova, which already brought the anomalous Hall effect into the connection of the barrier curvature, and mention also that you can look for Heusler compounds, because this is not so simple as the people thought, that the anomalous Hall effect scales simply with the magnetization. It goes beyond. This is even more interesting in antiferromagnetic materials, and I took simply here Heusler compounds. If you look for a normal simple antiferromagnetic Heusler compound, and you calculate here the anomalous Hall conductivity, you see, so for each spin direction, you have high values, but if you sum it up in a normal antiferromagnetic, in a collinear antiferromagnetic, it goes to 0. So even if you dope it, it doesn't help, and this is why people thought, so if the magnetization is 0, the anomalous Hall conductivity is 0, and the anomalous Nernst effect is 0, until I think in 2015, okay? So, and can we do something useful? And I simply want to say this is, yes, I think we can open a totally new field of thermoelectrics, and I think with topology and thermoelectrics, so magic number in thermoelectrics is a figure of merit, is a SETI, and people think if you go above figure of merit 3, this is no meaning value for you, but simply as a message, so then we are competing with oil and gas, okay? So, and there is a general understanding in thermoelectrics of normal materials that the CT cannot go above 1. So now people did a lot of engineering of materials and phonons and so on to increase it. But I believe that with topology and the magnetic field, we can easily go beyond 3, I would say, honestly. So we have a material which has a SETI of 3. Anyway, in a magnetic field. So, and so this is strongly also connected to the story of topology, because the topological insulator bismuth selenide is well studied already before the time of topology, and why Bob Carver came up with the idea, why not look for bismuth selenide after people looked for bismuth. So it was very easy because it's still one of the low temperature best thermoelectrics, okay? So which means we measure the normal Seebeck effect for bismuth selenide, so we simply have the current and the temperature gradient in the same direction, and the Seebeck effect is above 1. The SETI is above 1, like 1.5 to 2 at around room temperature. Okay, so, but with the increase of topological materials, the Dirac semi-metal, and I will show not an example, but simply applying a magnetic field, an external magnetic field to even non-magnetic Dirac semi-metal can lead to a magneto-Seebeck effect, which enhances the Seebeck effect by orders of magnitude without changing the so-called Wiedemann-Franz law, which is a limitation why we cannot. So simply applying a small hard magnet to maybe classical thermoelectric material can already do the job. So we have 2 papers under review here. And then, especially with magnetic materials, I mentioned already the anomalous Nernst effect. It's a different kind of a measurement arrangement, and this is especially interesting for magnetic mild semi-metal, so which is like now also area of research where many people look for, and it's extremely interesting for magnetic Kagome lattices. Okay, so we have this is a typical figure of the figure of merit. So you have to optimize the thermal conductivity with a normal conductivity and the Seebeck effect, and then you get this figure of merit, T, and this depends strongly in one sense, and the figure is normally shown differently. Then you have the charge carrier concentration. Here you have to optimize the charge carrier concentration. But even with a magnetic field, you see you can further optimize this, and this is something which only very few people do. And this is here an example for a normal Nernst effect measurement, which shows that in this topological semiconductors, you see giant responses in a magnetic field. You see the response of the Nernst effect to magnetic field, even in non-magnetic materials, is large.
What is the PF? Yeah?
This is a power factor. So people like to, because it's very difficult to measure the thermal conductivity. So people, this is a SETI without. So SETI is like thermal conductivity, resistivity, and Seebeck, and the power factor is only Seebeck and resistivity. because the resistivity is very often related to the thermal conductivity via the Wiedemann-Franz law. Okay, so there is a limitation which probably can also be overcome, which people think about hydrodynamic flow of electrons, etc. I don't know. Okay, so what we're looking for, so if we have a magnetic material, we can have a soft and hard magnetic material. Everybody knows here. And if you measure the anomalous Hall or the anomalous Nernst, you see that the curves look very similar. So for soft, here again for soft and hard magnetic materials, you get this extra contribution, which in some sense that people thought it scales with the magnetization is simply also based on the similarity. And the same is with the Nernst effect. It looks like the magnetization curve in a magnetic field. So, but as you know now, there's a big part of this is based on the Berry curvature and the topological properties, which have nothing to do with the simple magnetization. So can we find further recipes, and can we find ways to find topological materials? One system where I would simply want to show it is everybody is looking for the ideal wild semi-metal to have not too many other bands. And there's a system like the europium cadmium arsenic. It's a semi-metal. Unfortunately, what you see here from Inge's soft photo emission is already, you see the bands, and you see the cut off here at the Fermi energy. So you see it's heavily doped. And it's very difficult to dope the material to the wild point. So therefore, you are not surprised that there are no nature papers about europium cadmium arsenic. So because nobody can really nicely prove the chiral anomaly because the wild points are here. Okay, and it's a low temperature ferromagnet. It's a ferromagnet, and why are people even more interested in magnets than in non-magnetic system? And I motivate maybe the oxides to look more into this, because you have many materials where you are at the borderline between metal and insulator, is because the ideal wire where you only have two wire points in the reciprocal space can be only realized in magnetic material, because the simplest band structure where you break inversion symmetry in a non-magnetic material always leads to 4 wire points. Okay, so people really would look more to magnetic materials where you are at the borderline to metal to insulator. And I always say my hypothesis is that the whole colossal magnetoresistance effect is also a wire effect. So you go to the crossing point, you go from insulator to metal, and in between, when you go through the crossing points, you have the ideal wire if you have magnetic material. So, but it's not a waste of time, because you can measure thermoelectric properties even in a magnetic field. So I don't want to go through these curves. It's a resistivity, conductivity, Seebeck effect, and everything. Here is the power factor, and you see already around the magnetic transition, the power factor shoots up. And so if you compare it, then you find power factors, and this is here only a power factor in order. So these are some of the magnetic materials. I have also the classical thermoelectric here. So you see the power factor is orders of magnitude higher. Okay, so looking more for this material, even to think about new ways of finding thermoelectric materials in topology is really something interesting to do.
Sorry, Claudia, this was calculations or?
No, these are measurements.
Those are measurements.
So these are measurements. But you know, the application is limited. You can have a super power factor at 25 Kelvin. It's like, you have to find it at room temperature. Okay. I think in cadmium arsenics, they can also go quite high with the power factor. I simply want to motivate. We are interested mainly, we don't do thermoelectrics, honestly. We do the physics and measure the thermoelectric. We don't optimize the compounds, but more and more people, you can show that it's even interesting for thermoelectric application. So going now finally to the Kagomes is like, so for us, so it was more or less naturally, so because, you know, we like Heusler compounds, and so if you grow the single crystals of Heuslers, you have competition in the phase diagram. So you can get a tetragonal version of a Heusler compound and the hexagonal version of the Heusler compound. And people already put a lot of effort in investigating this phase transition, because these are shape memory alloys and these are magnetocaloric compounds. So people like Goodfleisch are working on this, and they are thinking they are even better than thermoelectrics. Okay, and they already found companies on this transition too. And this is simply a structural distortion of the Heusler compound, so along the 1, 0, 0 direction, but you also can have a structural distortion along the 1-1-1 direction, and then you end up with a Kagome lattice. We didn't recognize this. We simply, at a certain point, you want to have cubic ones. At another point, you want to have for MRAM the tetragonal ones. So, but we have known that if we grow crystal, so depending on the temperature profile, we can have a tetragonal, hexagonal, or cubic one. Okay. So, but suddenly we recognize also the hexagonal is very interesting if it's antiferromagnetic and the magnetization is in the plane, because you can have this frustration. So we looked a little bit more deeper in this manganese-rich compounds at the time where we were interested in MRAM. So Manuel knows, so we looked for MRAM compound, and we found, so you can have many interesting antiferromagnetic arrangement, and also here. So, but there are, and this was work which we did with Jürgen Kübler together, and this was the starting point. So we looked into this already in 2013, and then we recognized in some calculations that we get here an anomalous Hall effect and a Berry curvature, and this was for us unbelievable. And Stuart said, okay, forget about this. If you have a zero magnetic moment, an antiferromagnet, you cannot have a Berry curvature. You guide us mistakes in the calculation. And Jürgen Kübler was one of the people who did in his program that you can calculate the Berry curvature at the time when nobody was interested. Anyway, so this Kagome lattice is so this manganese germanium is more or less connected with a big family of Kagome lattice, and this is the first part already, where, for example, George Shekelski does a lot of work where he thinks he can even tune the dimensionality, and he worked mainly on these iron compounds a little bit later after our manganese-free tin, because they were also interesting. He recognized also that there are interesting topological properties, and some are ferromagnetic and some are antiferromagnetic. So it's again already starting that you can play around with the composition, and tells you already that there are many Kagome lattices in this metallic. So we looked here in a different class of materials because of all the things which I already told you, the Van Hofer singularity, the flat bands, and all the magnetism. And I simply can give you a few examples now about these compounds. But ignore maybe the compounds, okay? So with manganese-rich germanium then, and MacDonald found in manganese-free iridium that he also found anomalous Hall conductivity and a Berry curvature. So when we heard about the data from Alan MacDonald, we published the paper without Stuart and without Ben-Hai, who didn't believe us. And then suddenly we made the data, and Nagazuchi, after the theory publication, Nagazuchi published this Nature paper where he showed that there is an anomalous Hall effect even in a material which has no magnetic moment, or a tiny little non-compensated in this hexagonal antiferromagnet. And now you can imagine, you remember there was this crossing point, you have an anomalous Hall conductivity and an anomalous Nernst conductivity, and this was then the work of Kamara Benyan and the work of Nagazuchi, who showed also that you can have a large anomalous Hall effect. And this is a anomalous Nernst effect versus a magnetization, and now you see why people thought it goes linear with a magnetization, simply because all the data in the past nicely fitted into this scheme, and now you see manganese-free tin is orders of magnitude larger because of the Berry phase. So the Berry curvature in materials simply adds something which is also very interesting for thermoelectrics. Okay. So, and it's orders of magnitude. And we have to say in this antiferromagnets, the values are quite small, the magnetization, but you see you reach already the highest values of normal ferromagnets. So therefore, people thought that anomalous Nernst effect was not interesting for application until, I would say, now. Okay, so we looked also for ferromagnetic, so you can then even increase the family by taking 3 elements, and this is because my background is also in chemistry, so we are not scared. So I told you already manganese-free tin, then George Shekelski from MIT is working on iron tin family. So we thought, okay, let's look for other materials, and we came across to this even nature crystal, so which has a Kagome lattice, and it's out of plane magnetized, and it has this kind, and here you see nicely also in the properties, the magnetic properties, because it's a hard magnetic compound. So the first thing I told you what the referees, and the editor wants us to measure the chiral anomaly so that you can have, depending from the orientation of the magnetic field, in plane or out of plane, a negative magnetoresistance or positive. We measured it, but we didn't believe in it. Okay, sometimes this is like in this fancy journals, they make up your paper. Okay, we simply wanted to have this nice compound, this Kagome lattice with a large anomalous Nernst effect and Hall effect. Anyway, what we then also looked at, we have Fermi arcs here, and that we have a wide semi-metal. So you see the upper data from Julian Chen on our crystal, where you see also here the Y points are slightly above the Fermi energy, but here it was possible to dope it with potassium on the surface, so you can change and convince the referee that this is a fancy paper. Okay, so it doesn't end up in Nature Com or less. It ends up in a nice Nature Physics, at least, or Science, and you could nicely show that you see the Fermi axis like was predicted. And then the nice thing in non-magnetic materials, the Fermi arcs are very close to each other. In magnetic materials, the Fermi arcs are much larger, which is nice for photo emission. In chiral materials, I'm not talking today about chiral materials, they are even going all over the Bryan zone, they are even bigger. Okay, so anyway, so then you do the anomalous Hall conductivity, and here's a slide also some concepts which are related also to this paper, which I already mentioned about anomalous Hall effect. So in spintronics, people distinguish between the intrinsic, nowadays the intrinsic anomalous Hall effect related to the Berry phase, and non-intrinsic parts which are based on skew scattering or impurity scattering. And this can be done by looking of the ratio between rho h and x, y, and xx more or less, and then how it scales. And then you can distinguish these certain parts, and you can then always see whether what you measure, like here the cobalt 3 tin 2, have not too many extrinsic effects. They are really in this intrinsic area. And it shows a nice, very large anomalous Nernst effect. For ferromagnet, not as surprising, but this is was one of the first wide semi-measured experimentally. And you see now, so there all these wide semi-metals now, later it was clear that this also topological wide semi-metals are orders of magnitude larger than what is known from the normal magnets. A side effect is then, I already said, we are super interested in looking for quantum effects, because this is a really good way to prove properties. And if you go to lower dimensionalities, I think this is probably also the motivation from the MIT group on the iron Kagome. So you can eventually become more and more two-dimensional. And in two-dimensional system, we expect then that we really can measure in a truly two-dimensional quantum anomalous Hall effect. However, here in 3D materials, if they become quasi-two-dimensional, so we ask the question, can we imagine that a crystal of us is simply a stack of layers of quantum anomalous Hall effect? You tell me how. I have time, no? And indeed, so if you simply look for the quantized value in this quasi-two-dimensional materials, they come quite close to this quantized value. And then Vidya's group looked in SDM on our materials at the edges of this material, of the cobalt edges. They see really by changing the bias in the SDM values which are close to quantization. Anyway, so can we have more compounds? Can we become more confusing for the physicists? I know I tortured already the people in spintronics by having always 100 different compounds in my material. So first of all, the simplest Kagome lattice for people like Andre was, let's go back to hexagonal iron germanium. And this is the band structure which you have seen. And think about, can we understand the band structure of iron germanium? And by simply looking for the pattern which we have here for the Kagome lattice, crossing point, flat bands, Van Hove singularities. And in iron germanium, you can really take the d orbitals of iron germanium and make 3 packages out of the d orbitals. Okay, one is s and dz square, the other is dxy and xz, yz, and the other is x square minus y square and xy in the xy plane. So here, and this is like a kind what I would maybe call then a sigma type of bonding and so on. And if you make this pattern, and if you make a tight binding model, you see very clearly here nicely, you see simply the ideal band structure in the tight binding model. But if you compare it then with the corresponding bands in the real band structure, it's really still very close to this pattern with the crossing points, the flat bands, and this looks a little bit more complicated, but you still can do it. You see very nicely still the similarity between the tight binding model and the DFT calculation. So this helps already and shows also nicely that this theoretical simplified picture is not far away from reality. Okay, so then you can even go, and I told you already, it's the iron tin story already from Tchaikovsky and so on. Then you can go, even this iron germanium structure can be expanded to a giant family of hundreds of compounds, 500 or something, by simply making a oh sorry, this is wrong, this should be a 166 compound by stacking 2 or 3 layers of iron germanium on top of each other and putting something in between, okay? Then it becomes maybe eventually interesting for silk because you can have also rare earth and some cerium compound. And you see at the end, so you can connect still these band structures. Here's this more complex band structure still with the tight binding model in a sense to this pattern of orbital clusters and so on, to understand really the band structure in a simple way. Again, these materials are interesting for thermoelectric properties. Okay, so since I have still some time, I can show you. And my people, they are, especially the chemists and material scientists, they're always running for record values. Okay, I'm a little bit tired of this, but they make 5 crystals. They come as a postdoc, make 5 crystals, measure them, and try to get a record value of in an antiferromagnet at room temperature and so on. Anyway, so it shows really nicely that all this material shows also in helical materials nice values for the thermoelectric properties related to this interesting magnetic pattern. So I think, and I have to say, we really can make very, very high quality single crystals. This is one example. So the vanadium compounds are very interesting because I show later there are examples for superconductivity where people are talking about, and it's really nice. So you can really have high quality single crystal where you see very nice quantum oscillation, which helps you then to see really the band structure. This is a compound which has this vanadium, but it's not superconductor, while other Kagomes are superconducting, so not yet fully understood, but people are very interested in this and investigating this. Anyways, this compound shows also an instability, and this is especially of interest for the people looking for superconductivity. It shows a charge density wave instability, and if you have Van Hove singularities naturally in the band structure and all these Kagomes, now we recognize, probably we have overseen hundreds of charge density waves. Many of them probably have charge density waves, so which is very nice. So you have the ingredients like the charge density wave in this compound, but not the superconductivity yet. So and this can be really understood. I don't know whether this. So you can do experimentally looking what is the phonon instability, and this we do together with Andrei Bernovic and Santi. And we look here in this compounds, we have a phonon instability in this Kagome lattice perpendicular to the lattice. And you really see it nicely in the DFT calculation. You can even see the instabilities and predict which instability you have, phonon instability, and which charge order parameter you have in this material. So it's really a nice toy ground for finding probably interesting materials in topology, but also for superconductivity. So if you think about phonon instabilities, the Kagome lattice offers many possibilities. As you see here, this is simply a theoretical paper which It was done by our Spanish friends together with Maya and Philip, who are working all in this field now with us together. So you see, you can find very interesting pattern, including what interests me and Marco, chiral charge density wave. Okay, so there are many, and you see there are many possibilities. Since the band structure is full of charge of Van Hove singularities, flat band, so it's like an inflation also of interesting instability. So Shandong Feng in my group together with Andre, he investigated, now you can see, all kinds of 166 compounds. And now you can see how many you already can look here, and it's not the full list. So here we don't have the nickel compounds where we're looking too, because we expect the vanadium compound and the nickel, since they are not magnetic, probably nice for superconductivity. The manganese compounds are interesting because we are still looking for antiferromagnets which have strong anomalous Hall response because of the frustrated magnetism. So I didn't say, but we now know if we have non-collinear spin structures in the antiferromagnets and they are topological, they are all frustrated and they all show very nice Berry phases so far. Yeah.
These are the critical temperatures?
Yeah, these are the Curie temperatures. The nice thing is the Kagome, my people like room temperature, okay? They write to patents. Yeah, they're all above room temperature. So they're all interesting, okay, above room temperature. And so we avoid cerium and all the interesting stuff for Silke because it's her job and not our job. And it's not possible to do it properly with DFT, okay? Yeah, ytterbium. I think in ytterbium sometimes it's better because you can get the fully, or not too much not so much disturbance. So I think ytterbium because my people like to make it. Anyway, but you see then what we could identify in these structures, different kinds of instabilities. So this was already shown for this example, which I showed before. This was the iron germanium, I forgot. Anyway, so there is an instability between the germanium in this compound. And so we have type 2 and type 3, which is even interesting because it makes the Kagome lattice slightly twisted. Okay, so, but this happens by nature. So you don't do twisting, okay, in this material. And these are the type 1, which I love because it's chiral, okay, to have a charge density where you can switch on chirality. And one chirality versus the other chirality is interesting. So now you see that only the black ones are stable up to low temperature, okay? So now you see there's an inflation of instabilities, okay, which is not surprising because the band structure is full of Van Hove singularities and so on. So this is a theoretical prediction. Now my group is very active growing single crystal to see, and these are the different kinds of phonon instabilities and so on. Okay, and these are examples, as I mentioned before, some which has this phonon instabilities here are reflected then that the Kagome layers are slightly twisted. This is was published and recognized by the group here, former student involved of mine, Barry, and her new team. So you can see already in the structural distortion of the material. So here it's static, it's not dynamic. So, but you can see nice twisting of the Kagome lattice as a result. So what is the outlook? So there are thousands of undistorted Kagome lattices, but you can even try to understand whether there are interesting distorted Kagome lattice by studying the structure, substructures, and so on from the viewpoint of crystallography. And there's one interesting system. This is this holmium silver germanium with a very nice recent paper also on some interesting magnetic properties from the group of Philip Gebenwart, so which has drawn the interest of my group, which shows also very nice, interesting structural transitions and properties. So which shows simply if you look then for more compounds which show more interesting instabilities, you can go to the distorted one. And my people simply had the motivation, so if you distort it, you go from Dirac to Weil in a natural way. And they looked again for the anomalous Hall conductivity and for the anomalous Nernst effect. And this is simply here, again, interesting. It goes even above the Néel temperature in this compound. But it shows simply that you can reach out in many areas. And there's a new paper from Philipp Gegenwart in Nature Physics also 1 or 2 weeks ago about the interesting magnetic materials. Okay, so like going back to Marco, okay, we like chirality, so, and maybe twisting graphene is a way to get chiralities and homochiral materials, but also this chiral charge density wave system, there is quite also a little work of Hassan. In this way, you can switch the magnetic field, and with switching the magnetic field, you can switch the chirality. So, and this is more a structural chirality, but it's the question is, can we have, or is there a relation between electronic chirality and the Weil physics and the chiral anomaly and the structural chirality? One nice example here is also, and this is my last slide, but simply showing this is also Kagome lattice, and it's not related to 1, 1, so the composition. So there are also 1, 3, 5 composition, which are a big family of Kagomes. There's a 1, 3, 4 composition, which are a big family of Kagomes. And here, this is now a hot topic in the field of superconductivity, because this is a superconductor with people think evidence for chirality at low temperature and superconductivity and charge density wave instabilities and 2 different charge density. So also I have collaboration here with the people, and the nice thing what you see is like what I like to do more, and we only can do with Philipp because it's not so easy to measure, that you go to a higher order transport measurement, because then you can measure the magnetoelectric effect, which for me is a nice way to measure whether something is chiral, okay, and whether you can switch the chiralities then nicely. And this was done here on this compound by simply switching here's for different magnetic fields, measuring the different angles and so on. This is ongoing work with Philipp. But you can see here also he makes these very nice devices where you have not so high conductivity, which are the precondition for measuring the magnetoelectric effect below then the charge density wave transition. But what he also found out is that it's very strongly related to strain. So if we strain the compounds, we can enhance this chiral effect, or if we apply a magnetic field, we can induce the chiral effect. It's only there when there's a magnetic field or strain, and it's not there when a lattice is pristine, but it shows also that if you use even external fields, forces, whatever, in this Kagome lattice, you can get even more interesting stuff by design. So with this, I come to the end. So there are more materials where you can have flat bands and interesting instabilities. So like it goes beyond the Kagome lattice. So there's a big list now published, I think, last year with more compounds and more prediction. And with this, I come to the end. So I hope I convince you that you can have with the Kagome lattice, a metallic one, a very nice field where you can play with electron correlation, topology, and magnetism to see all the things which you know from correlated physics. The people in high TCs know this, with things which you know from spintronics. And so it merges more topology with spintronics and high TC researchers. So we all can come together and work on Kagome lattice. And with this, I thank you for your attention. Thank you very much. I'm Michael.